So let's continue with the momentum and ask for eigenstates of the momentum. So eigenstates of P. You know them. They're e to the IPX things. So let's write them with some convenient normalization. This denotes a wave function that depends on x with momentum p. And we'll write it as a definition as e to the IPX over h bar. And I'll put a 2 pi h bar here. It's kind of a useful normalization. Then p hat on psi p of x. Well, p hat is supposed to take h over I ddx and take h over I ddx of psi p. And the h over I cancels the I over h. When you take the ddx, you get p out, and you get the same wave function. So indeed, you get p times psi p of x. So indeed, this is the eigenstate of the momentum operator, and it has momentum p. Well, what is the use of this? Well, if you say you have a representation, what we call the position representation of the wave function and operators, let us think now of the momentum representation. So what does all that mean? Well, there is the Fourier transform operation in which we have psi of p. Well, let me write it this way, actually. I'll write any psi of x physically can be represented as a sum of momentum eigenstates. Therefore, that's Fourier's theorem, minus infinity to infinity dp e to the IPX over h bar, square root of 2 pi h, psi tilde of p. That's Fourier transformation, defines psi tilde of p. And Fourier's theorem is the fact that not only you can do that, but you can invert it so that psi tilde of p can also be written as an integral, this time over x, from minus infinity to infinity, e to the minus IPX over h bar, also 2 pi h bar, psi of x. So let's ponder these equations for a couple of minutes. Well, this is, as a physicist, you think of this, well, this is telling me that any wave function could be written as a superposition of momentum eigenstates. Here are the momentum eigenstates, and for each value of momentum, you have some coefficient here that tells me how much of that momentum eigenstate I have. Now, here is the opposite one. Psi tilde of p and psi of x are related in this way. So these coefficients, if you want to calculate them, you calculate them this way. But now let's think of it as a change of representation. The physics is contained in psi of x. All what you wish to know about this physical system in quantum mechanics is there in psi of x. But it's also there in psi of p because they contain the same information. So there are different ways of encoding the same information. What is the relation between them? This, we thought of it as a vector in position space, an infinite dimensional space that is talking about positions. this is another vector in momentum space. Just P, think of it now, the infinite line. So this is an infinite vector with all those points, little by little, from minus infinity to plus infinity, all of them there. Gigantic vector. And here is another gigantic vector with P from minus infinity to infinity. And in between, there's an integral. But now, with your new picture of quantum mechanics, you see an integral, but you also see a matrix. And what is this matrix? Think of this as some sort of psi sub p. And this as some sort of matrix p x psi x, in which, if you have a product, you remember when you multiply matrices, matrix on a vector, you sum over the second index. That's the product of a matrix. And then the first index is the index here. So here is what it more or less is like. Psi tilde of P is obtained by this, and this matrix depends on two labels, P and X, and it's that. So it's a matrix full of faces. So how do you pass from the coordinate representation of the information, a vector of all values of the wave function in all positions? By multiplying with this matrix of faces that is here, and it gives you this representation. So different representations means using different vectors to represent the physics. And this vector is a very nice one, and because of these properties of the momentum operator and all these things, this vector is also a very nice one. And there's an integral transform or some sort of infinite matrix product that relates them. And we shouldn't be uncomfortable about it. That's all fine. So we say that we have, for example, psi of x as one representation of the state, and psi tilde of p as another representation of the same physics. We can do one more thing here. Continue. We can take that boxed equation on the blackboard up there and act with h bar over I ddx on psi of x. So that is equal to hi ddx, and I'll write what psi of x is minus infinity to infinity dp e to the I px over h bar square root of 2 pi h bar psi tilde of p. Now, when we act on this, as you know, h bar over I ddx just acts on this and produces the factor of p. So this is equal to minus infinity to infinity dp e to the I px over h bar over square root of 2 pi h bar p times psi tilde of p. So look at this equation again. This double arrow is to mean that there are equivalent physics in them. They have the same information. It's the same data encoded in a different way. And that different way, this arrow is Fourier transformation. And this Fourier transformation is explained here. So now you have Fourier transformation the same way. So here we have, what we've learned is that h over I ddx of psi is represented in momentum space by p psi tilde of p. And this was p hat acting on psi of x. So the corresponding thing in momentum space of p hat acting on psi of x is p multiplying psi tilde of p. Which is to say that we can think of the abstract operator p hat acting on psi tilde of p as just p psi tilde of p. So in momentum space, the operator p hat acts in a very easy way. In coordinate space, it takes derivatives. In momentum space, it's multiplicative. So in position space, x is multiplicative, but in momentum space, x would not be multiplicative. X would also be a derivative. So I leave it for you as an exercise to show that, or convince yourself in several ways that x hat is really I h bar ddp in p space.